Hi, hello, namaskar. Myself Mahesh Prasad from Department of Physics. As you know, well, dear students, we are in a topic that is nothing but a new chapter we are going to deal today. That is nothing but thermodynamics. What comes to your mind when I say thermodynamics? By looking at the term, the thermo which indicates what? Which is nothing but a kind of heat. What do you mean by dynamics? What do you mean by dynamics? Dynamics which indicates it's a kind of motion. So what is in motion right now? The heat is in motion. So this is a chapter where we are going to deal especially in terms of the heat transfer or the heat transfer from one place to another place, and also we can deal the conversion of energy. It's like the energy from one point to another point, like the basic conversion between the heat energy into mechanical energy, vice versa. Okay, and and this is a chapter where we are going to deal the principle behind the refrigerator which you are using at your home, and how your principle or how the refrigerator is going to work, and how is it possible to make the inside temperature as colder than the outside, and what could be the principle behind the physics, what is the physics behind that particular the phenomena over there. So this is the basic concept we are going to deal under thermodynamics. So before we get into all those phenomena, we need to understand the basic terms which is going to helpful to understand more clearly about the concept over there. So that we'll start up with the test class and nothing but so before we get into this, we need to know a few basic terms that which we are going to use randomly in all the concept in this particular topic. Okay, the first things which comes to your mind, that is nothing but a system. That is nothing but thermodynamical system. So what comes to your mind? There is a definition which is under this. So before that, I'll give one experimental observation. What is there in my hand? Kind of cup you can observe, right? Now, what I'll do here is that I'll pour a water somewhat like this. So, inside the cup, what is there now? What is there? Obviously, the water, correct? Now, don't you think this water will take a shape of the container? Yes. Now, you go through the definition which is there on the board based on the thermodynamical system. It is nothing but it is a collection of extremely large number of particles confined within a certain boundary. In the sense what? Don't you think this water which is there inside the cup, don't you think this liquid which is made up of n number of particles? Are you getting? So now, don't you think this n number of particles are confined within a certain boundary? What is the boundary for this water? Obviously, the cup is the boundary for this particular water. Now, what I can say here is that, don't you think the water which is there inside the cup is a system? Yes or no? According to our definition which is there on the board, it is nothing but thermodynamical system which indicates or which defines. It is a collection of extremely large number of particles confined where? Within a certain boundary. What is the boundary for this? For our example, that is nothing but a cup over here. Now, the one more the term which we are using, that is nothing but a surrounding. Surrounding which indicates what? Anything outside the system is called as what? Surrounding. So don't you think for water or a liquid which is there inside the cup is a surrounding? Yes or no? So now, anything outside the system is called as what? Surrounding. So this is what exactly we are supposed to remember when I say system. A system is a collection of extremely large number of particles confined where? Within a certain boundary. What is the boundary for this? Cup over here. Okay. So what do you mean by surrounding? Surrounding which is nothing but other than the system is called as surrounding. Okay. That is the one thing. And now the one more thing you have to remember, that is nothing but adiabatic, two different walls we can find, especially whenever we construct different laws. I am using two types of laws. I am using two types of walls over here. Okay. The first wall which comes, that is nothing but adiabatic wall, and one more we have, that is a diathermic wall. We will see what exactly the adiabatic wall. Adiabatic wall in the sense, it is a kind of wall which does not allow a heat can transfer from one place to another place. Okay, so I'll show you. And if I take one now, I have taken one isolated or insulated, the insulated boundary for this, somewhat like this. Okay. Now I will make a two part between this. The one is this, and this is a wall I am keeping, that is nothing but the adiabatic wall. So this is the adiabatic wall I am keeping over here. Okay. Now what I do here is that, and there is a water. There is a water over here. Okay, and this is the point A, and let us say this side which is maintained at temperature A, and this is the B. Now, according to our definition of adiabatic wall, what do you mean by adiabatic wall? It is a wall in which doesn't allow a heat can transfer from one point to another point, or one medium to another medium. Now, this is for example, if where A is a system. What do you mean by system, by the way? It is a collection of extremely large number of particles confined in within certain boundary, correct? Now, this A is one system and B is one more system. Do you think a transfer of heat will take place if I say this wall is the adiabatic wall? This is the adiabatic wall. Do you think a transfer of heat will take place? No, because adiabatic wall is a kind of insulated wall over here, or adiabatic wall in the sense it doesn't allow heat to transfer from one system to another system, or one place to another place. Why? Because it is a wall, it is an adiabatic wall. So remember this, whenever I say adiabatic wall, your job is to remember what you supposed to remember. It is a kind of insulated wall which doesn't allow a heat can transfer from one point to another point. Are you getting? Well, and one more wall we can find, that is nothing but diathermic wall. Di means what? Two, right? So we'll do that. I'll take one more wall over here, the kind of insulated wall. Obviously, you supposed to take two different systems, let us say system A and system B, and these two systems are separated by a diathermic wall. What do you mean by diathermic? It is a wall in which can allow a heat can pass through it, or it can allow a heat can transfer from one system to another system. So obviously, we supposed to get the two systems somewhat like this. Let us consider two systems. That is the system A and system B over here. Now what wall you have taken? That is nothing but the diathermic wall. So what do you mean by diathermic wall? If it can allow a heat can transfer from system A to system B. So that's why it is a non-insulated system or non-insulated wall over here. What do you mean by adiabatic wall? It doesn't allow heat can pass through from one system to another system, or system A to system B. So whenever I use adiabatic wall, you supposed to remember it doesn't allow heat to pass through it, and whenever I say diathermic wall, it can allow heat through one system to another system. So this is the basic relation. We suppose to know more about one more law, which is called as Zeroth Law of Thermodynamics, that we discuss. The one more law which we are going to deal, that is nothing but the first law in thermodynamics, that is nothing but Zeroth Law of Thermodynamics. Okay. So Zeroth Law of Thermodynamics, which is basically it is how the temperature is going to plays a major role in thermodynamics. Okay. So according to this particular zeroth law, what it says that if two systems like A and B are separately thermal equilibrium with each other with respect to the other system with respect to C, then system A and system B are thermal equilibrium with each other. In the sense, we'll try to draw one diagram which is based on the law of zeroth law over here. So let us go with that. Along with the definition, let us consider two systems A and B are separately thermal equilibrium. So somewhat like this, which means let us consider two systems over here. Okay, we have taken two systems over here, and in between, let us say it is a system A. Let us say it is a system A, and it is a system B over here. Now I place one adiabatic wall between system A and system B over here. What is the wall? Adiabatic wall. What do you mean by adiabatic wall? Adiabatic wall is a kind of wall which doesn't allow heat can pass through it. Okay. So now, how many systems we have taken? Two systems. According to our definition, if system A and system B are separately thermal equilibrium with another system, that is the C. So which means one more system we need. So along with that, somewhat like this. So in between this, I'll keep one diathermic wall. What do you mean by diathermic wall? It can allow heat can pass through it, correct? Yes. So I'll place the water or any fluid with the system C over here. Okay. So now what is the wall we have? So altogether how many system we have? Three. There is nothing but A and B and C, and look into the figure which I drew just now. A and B are separately thermal equilibrium with respect to what? System C. Now can I say if I maintain the A as for example 10 degrees Celsius, and if I say B as 20 degrees Celsius, and if I say C as 30 degrees Celsius. Now, don't you think when I say thermal equilibrium, at the end, all the systems should have an equal temperature. Then only I can say these systems are in equilibrium. When I can say these three systems are in equilibrium, look into the figure. If system A and system B are separately thermal equilibrium with respect to what? System C, and how these are interconnected. A and B are interconnected with respect to adiabatic wall. So direct heat cannot flow from A to B, but there is a way that heat can flow from A to B through C over here. Why? Because we have maintained a diathermic wall. Diathermic wall between these two systems with respect to C. What is this system? Adiabatic wall. So, according to the law of zeroth law, if system A and system B are separately equilibrium with the which system? System C, then we can say system A and system B are thermal equilibrium with each other. It's just like if A is equal to C and B is equal to C, so can I write A is equal to B over here? It is as simple as basic mathematics. So that's what here temperature plays a major role in terms of thermal equilibrium. So this is what exactly we can find under the law, which is nothing but zeroth law of thermodynamics. Okay? Right. Well, dear students, before we move into the first law of thermodynamics, we need to see some of the thermodynamical state which is going to helpful to understand more about the first law of thermodynamics. The first one, that is nothing but the heat, is a familiar word for you, and also we are supposed to deal the work done, and the next one is supposed to deal, that is the internal energy. Okay. The first one, what do you mean by heat in terms of thermodynamics? So the basic definition we know that is nothing but heat is a form of energy which can flow from body at high temperature to lower temperature. Similarly, the energy that is transferred between the system and the surrounding, hope you know the word of what is in the system as well as surrounding, that we have discussed in the initial stage of our class. And if the energy is transferred between the system and the surrounding, whenever there is a temperature difference between this, in the sense, you take one, the chamber somewhat like this, with the movable piston somewhat like this. Okay? Imagine there is a gas particle inside the chamber with the movable piston over here. Now, what I do here is that, with respect to our discussion, whatever which is there inside the chamber, we can call it as a system. Correct? Yes. So this is the system over here, and whatever the other than system, we can call it as a surrounding. Correct? Yes. Now, according to our definition of a heat, there is a change in energy will take place between what? System and surrounding. And when it is possible? When there is a temperature difference between a system and a surrounding. For example, if I maintained around 80 degrees Celsius as a system temperature and 50 degrees Celsius as the surrounding temperature, obviously, how would your heat can transfer? Whether it can transfer from surrounding to system or system to surrounding. Obviously, you know heat can transfer from body at higher temperature to lower temperature. So, if the heat is transferred from higher temperature to lower temperature, obviously what happens? There is a change in energy will take place. What kind of energy? There is nothing but a heat over here. Okay? So this is what exactly we can find. And one more thing we are supposed to remember, there is a work done. So during this process, don't you think if heat is going to lose by the system, since we have a movable system, in the sense this is it can move up as well as down over here. If the system is going to lose the energy, in the sense what? Don't you think a decrease in volume will take place? Obviously, whenever I speak in terms of work done, we are interrelating with respect to its volume. So whenever there is a decrease in volume, what happens? This piston can move downward over here. So obviously, what happens? Decrease in work done will take place. Okay? So according to the definition of work done, what we can say? Work is done or work is said to be done when if a body of a or a system moves through a certain distance with a particular direction. Okay? Whether it could be work is done, positive work done or negative work done, we'll get to know based on its sign convention later. Once we'll get into first of thermodynamics. For time being, your job is to remember, if there is a decrease in volume, what happens? Obviously, the piston moves downward. If there is an increase in volume of a system, what happens? There is a increase in work done will take place. Why? Because the piston is moving upward direction. Okay? Fine. And one more thing is supposed to remember, that is nothing but the internal energy. Internal energy of what? Internal energy of a system. And basically, your internal energy, which depends on the two major factors, that is nothing but kinetic energy as well as its potential energy. By the way, what do you mean by kinetic energy? The energy possessed due to its motion. What is in motion right now? Obviously, the gas particle is in motion. When your gas particle can get a motion? When there is an increase in temperature. Okay? So, always we supposed to remember, whenever we have an increase in temperature, obviously these particles are in motion. Whenever we have a motion, it can gain a kinetic energy. Whenever there is an increase in kinetic energy, obviously there will be increase in internal energy. All these things are interrelated. Like internal energy basically depends on the kinetic energy. Normally we have a potential energy as negligible for this particular case. We mainly concentrate on kinetic energy over here. And kinetic energy depends on what? temperature. If temperature increases, kinetic energy increases. If kinetic energy increases, obviously the internal energy is going to increase. Okay. So this is what exactly we can find the basic three thermodynamical state. Before we get into which law? First law of thermodynamics. Okay. Which are the three things? That is the heat or heat energy, work done, and internal energy. Okay. Fine. Well, dear students, we are in a topic that is nothing but first law of thermodynamics. So, what it means, first law of thermodynamics? Basically, here it works under the law of conservation of energy. Law is means energy is conserved. Okay. So, how we discuss? So, according to the first law of thermodynamics, what it says that the heat supplied to a system, in the sense, will take one chamber. Odd lines with the movable piston. The piston we are having with the movable piston. Okay, fine. Let us imagine there is a gas particle inside the chamber over here. As a system, what do you mean by system? Is a extremely large number of particles confined within a certain boundary. Correct? So, what is the boundary? This is the boundary for this. What is the system? Inside the boundary over here, and this piston is a movable piston, and you know when it can move, when it can place in a stationary position. Okay. Now you have applied a heat. What you have applied? Heat energy to a inside the system. Obviously, whenever the heat energy is supplied to a system, which can be utilized, the part which means dQ, I can say, is the heat energy supplied to a system which can be utilized in two ways. The part of energy which is utilized to do what? Increase the internal energy, which means dQ is equal to du. Du which indicates what? Internal energy. Okay, du is called as what? Internal energy, and the remaining heat which is utilized to do what? To do work done. To do work done, there is nothing but a dW over here. dW, this is nothing but work done by the system. Why by the system and on the system, you will get to know. And whenever right now I have applied a heat energy to a system, obviously there is an increase in internal energy will take place. Increase in internal energy in the sense what? Obviously there is an increase in temperature. If there is an increase in temperature, there is an increase in kinetic energy. If there is an increase in kinetic energy, obviously there is an increase in internal energy. So that what happens? At this particular moment, don't you think this piston is moves upward or downward right now? If there is an increase in internal energy, obviously there is an increase in volume will take place. So if there is an increase in volume, don't you think this piston moves upward or downward? Obviously it should move upward in direction, which means work is done by the system. So this system is doing a work over here. Okay? So that if work is done by the system, what happens? This system is going to expand. So if there is an expansion, means there is increase in volume. Volume is which is basically deals with what? Work done over here. So this is what exactly we can find, especially under the concept of first of thermodynamics. And now we will get to know when this dQ is positive and dQ is negative in terms of sign convention. That is nothing but the sign convention. What do you mean by sign convention? And you will get to know. And especially this is used to while solving a numerical as well. So when dq is positive, when dq is negative, when dq is positive, dq is positive if heat supplied to a system. Heat is supplied. Heat is supplied. When we have dq as a negative over here, when we have negative with respect to dq, the heat is absorbed. That is the heat absorbed. if heat is absorbed by a surrounding, which means what happens? There is a loss in heat. If this is a surrounding, if this surrounding absorbs the heat from a system, then we can say there is a decrease in heat. So if you subtract heat, what happens? There is a dq, which means plus dq we can have over here. That's what we can have over there. So which means